We're diving into a paper that tackles what is uh, arguably the single biggest bottleneck for deploying frontier embodied AI today.
And that's the crippling latency you get with these massive vision language action models, or VLAs.
Yeah.
The paper is Training Time Action Conditioning for Efficient Real-Time Chunking. It's from Kevin Black, Alan Wren, Michael Equi, and Sergey Levine at Physical Intelligence.
And their target is that inference time, right? The tens, sometimes hundreds of milliseconds it takes for a model like $0.66 to think.
Which, for a robot, translates directly into, jerky, non-reactive movement. It's just not good enough for the real world.
So for a while, the go-to solution was something called real-time chunking, or RTC.
Right, which used asynchronous action prediction. You'd start generating the next set of actions before you finish the current one.
But it had this big catch, this reliance on what they call inference-time inpainting.
And that inpainting step is the whole paradox. To get it to work, it needed to compute a vector Jacobian product,
Which is basically a backpropagation step.
at runtime. During every single denoising step, it added this huge computational overhead right when you were trying to save time. It just didn't scale well with higher delays.
Okay, so that brings us to the new proposal, Training Time Action Conditioning, or TTAC.
And it's such a simple, elegant shift in thinking. Instead of fighting the delay at runtime, just accept it's going to happen.
And you simulate it during training. You teach the model what that delay feels like from the very beginning.
Exactly. And the result is you completely eliminate that inference time overhead. It's a drop-in replacement that not only matches the old method on complex real-world tasks,
But it actually outperforms it when those system delays get really bad, which in the real world, they always do. Okay, so let's unpack that a bit more. I mean, we're all used to waiting a second or two for a chatbot to reply. Why is the difference between, say, 50 milliseconds and 150 milliseconds so critical for a robot?
it really boils down to the simple fact that a robot is an embodied agent. It exists in the physical world.
A chatbot can just pause and think.
Right. The world doesn't pause for the robot. If you're trying to do something dexterous, like catch a ball or, screw in a light bulb, you need a control loop running at maybe 50, even 100 hertz.
So you need a new decision every 10 or 20 milliseconds.
Every single time. And that creates this fundamental tension with where AI research is going.
The models are just getting bigger and bigger.
Billions of parameters are now the standard for these VLAs to get the kind of generalization we want. But bigger means slower. So you're constantly fighting this battle between the model's intelligence and the robot's need to react instantly.
We have seen other ways people have tried to tackle this, right? Things like hierarchical designs or just building smaller, faster models.
For sure. Things like Gemini Robotics or Mini VLA. But what's so interesting about the TTAC paper is that the solution is almost completely orthogonal.
You don't have to change the model's architecture.
Exactly. You don't have to shrink your VLA or build some complex hierarchy. This is all about the execution framework. It's about letting that big, powerful, high-latency model run smoothly just by teaching it how to handle its own sluggishness.
To really get why TTAC is so clever, I think we need to quickly go over how the older system, real-time chunking, actually worked.
It's worth it. So the base setup is your policy, your VLA, isn't just predicting one single action. It's predicting a whole sequence of future actions called an action chunk.
And that sequence has a length, h, the prediction horizon.
Right. And then you have two key timing parameters. The first is the execution horizon, which is ACE. That's just how many steps from the chunk you actually use before you ask for a new one.
And the second, the really important one, is the inference delay.
That's the killer. That's the actual wall clock time it takes the model to think. So if you ask for a new plan at time t, you don't actually get it until time t plus d.
And in that time, the robot hasn't been sitting still. It's been executing the first 8 actions from the previous plan.
Exactly. And that set of actions that have already happened while the AI is thinking, that's the action prefix.
So the whole challenge is making sure the new plan you just generated seamlessly continues from where the robot actually is after executing that prefix.
And that's where the original RQC hit its computational wall. It used something called pseudo-inverse guidance to sort of force the new chunk to obey the constraint of that prefix.
And that's where the expensive part comes in.
Yeah.
Why does enforcing that constraint require so much computation? You mentioned this vector Jacobian thing.
Well, it's because you're using guidance inside a diffusion model. You're basically calculating the error, the gradient between the prefix the model is generating and the one that actually happened.
Okay.
And then you use that gradient to steer the diffusion process. But to calculate that gradient, you need backpropagation. You're effectively doing a tiny training step, a backward pass on every single denoising step during inference.
So you're paying a huge runtime penalty.
A huge penalty. And it's important to remember, while it was expensive, that method did have one advantage: flexibility. It could do something called soft masking, which we can get into, but TTAC has to give that up.
Okay, so that sets the stage perfectly for the core idea of TTAC, training time action conditioning.
The insight is so simple. If this delayed is just a fact of life, stop fighting it at runtime.
Just build it into the training process from the start. Let the model learn to predict the continuation given the start.
That's it exactly. The learning objective literally changes. You're no longer just predicting the full action chunk, you're learning to predict the action postfix.
The part after the delay.
Right. The model learns the probability of the actions from step D to H, conditioned on the observation and the known action prefix from step 0 to D. You're just telling it, here's what you see, and here are the first few things that already happened. Now what's next?
That makes perfect sense. But it does raise a pretty big question for real-world use. Latency isn't fixed, right? It fluctuates all over the place. How does TTAC handle being a moving target?
And they have a really neat solution for that, too. They just randomize raw during training.
How clever.
For their real-world tests, they just pick a random delay uniformly between 0 and 10 for every single training sample.
So it teaches the model to handle anything from 0 delay up to a 10-step delay.
Yep, which on their 50 hertz system is 200 milliseconds. So by training on this constantly shifting prefix, the model just gets incredibly robust to whatever latency it happens to encounter during deployment.
So you're basically taking all that computational complexity that crippled the runtime of RTC and you're just moving it.
You're moving it into the offline training stage where it's basically free. And because the final output is still just a sequence of actions, it really is that seamless drop-in replacement.
All right, for the more technical folks listening, let's get into the weeds of how they actually implemented this. It just took 3 small but very clever changes to a standard diffusion transformer architecture. And this is based on the option expert from the TAT all to lens 6 model, which uses that A to lens 0 conditioning. So walk us through change number 1, which has to do with the time step.
Okay, so the first change is you need to allow the flow matching time step, which they call tau, to be different for every single action token in your chunk.
Why is that? Normally it's the same for the whole sequence, isn't it?
It is. But here, your prefix actions are fundamentally different from your postfix actions. One is known ground truth, the other is a noisy prediction. So to tell the model which is which, they allow the conditioning parameters in the Adelin 0 layers to vary for each position.
And crucially, this doesn't add any new learnable parameters. It keeps the model the same size.
No new parameters, it just changes how the conditioning is applied. And that sets the stage for change number 2.
Which I think is the most elegant part of this whole thing, using tau $1 as the signal.
It's so good. So for all the action tokens that are part of that prefix, the input is the clean ground truth action. And for those tokens, they set the time step tau to exactly 1.0.
And in flow matching, tau $1 means this is the clean data, right? 0 noise.
Precisely. It's an unambiguous signal to the model that says, hey, this part of the sequence is known. It's fixed. Don't touch it. So the model's entire job becomes learning how to denoise the postfix tokens, where tau is less than 1.0, based on those perfectly clean prefix tokens.
It's never even trying to predict the prefix, just continue from it, which I guess leads directly to the third change, the loss masking.
Exactly. If you're giving the model the prefix as ground truth, you can't penalize it for its outputs in those positions, so you just mask them out. The loss function is calculated only on the outputs corresponding to the action postfix. All of the model's learning is focused exactly where you need it, on the actions that haven't happened yet.
The implementation is really neat, baking the constraint right into the training data. So how did this actually perform in their experiments? Let's start with the simulation results.
The simulation on their kinetics benchmark really confirmed the whole hypothesis. It showed that this training time conditioning is just way more robust when you have large delays.
So TTAC beat the old inference-time RTC.
Specifically at delays of D equals 2 and higher. And as they pushed the delay up to 4 steps, the performance gap just got wider and wider.
And what's the intuition there? Why does the older gradient-based method start to fail so badly as the prefix gets longer.
It goes back to that Jacobian being a linearization. It's a local approximation of a really complex nonlinear system. As your constraint, your prefix, gets longer, you're trying to steer the model further and further away from its initial path.
And the linearization just isn't a good approximation anymore.
It becomes unreliable, the guidance starts to fail, and you get bad actions. TTAC, on the other hand, has actually learned the true, complex relationship between the prefix and the postfix over a whole range of delays, so it's just inherently more robust.
There was one tiny trade-off, though, wasn't there?
A very, very minor one. TTAC was marginally worse at delays of 0 and 1, and that's probably just because it's spending less of its training budget, on that specific zero latency case compared to a model trained only for that scenario.
Which is a totally acceptable trade-off since zero latency never happens in the real world.
Exactly. And speaking of the real world, they then deployed this on the big Tapena 666 VLA for some really hard tasks.
Yeah, these weren't simple pick-and-place things. We're talking about building a box and even making espresso.
Which involves grinding, tamping, pulling the shot, pouring. It requires really fine control. Any jerkiness, and you've got coffee everywhere.
So what were the numbers? What was the latency difference?
It was pretty clear. When they ran inference on a remote H100 server, TTAC averaged about 108 milliseconds of latency. That corresponds to a delay of about 5.
And the old method?
Inference-time RTC was notably slower, clocking in at 135 milliseconds, which is a deed of 7.
So the main takeaway is TTAC achieved the same success rate on these hard tasks, but it did it faster and more efficiently.
That's the key. Both asynchronous methods were way better than just running the model synchronously, which they said had visible pauses. But TTAC delivered that same fluid motion and task success while being fundamentally cheaper to run at inference time. It's a huge win.
So, connecting all this back to the big picture, TTAC seems like a really practical solution for deploying these giant models. It just accepts that latency is a reality and uses a clever training trick to work around it.
It's an excellent step forward, for sure, but it does bring us back to that one trade-off we kind of glossed over earlier.
Flexibility.
Flexibility. TTAC is, by its nature, much more rigid than the original inference-time RTC.
And that comes from how it's trained, with that hard signal of setting the time step to 1.0.
Yeah. It creates this binary condition. The prefix is either known or it's not. The old guidance-based method could do something called soft masking.
Which means?
It could softly condition on actions beyond the hard prefix, using, say, exponentially decreasing weights. It allowed for a more nuanced, gradual transition between what was known and what was being predicted. TTAC loses that capability.
And there's also the tuning problem, right? You have to make a good guess about what your real-world latency distribution is going to look like when you start training.
You're making an upfront commitment. If you train for delays up to 10 steps and suddenly your system starts seeing 20-step delays, the model's performance is going to suffer.
Which I think raises a really interesting, maybe provocative question for the future.
I think so. The question now has to be, how do we get the best of both worlds? How can researchers combine the raw efficiency and learned robustness of TTAC with the kind of nuanced, flexible control you can get from soft conditioning and inference time guidance?
Finding a way to get that cheap computation and that infinite flexibility.
That's the next frontier, a model that's both efficient to run and can adapt to any constraint you throw at it. That's what will enable the next generation of truly reactive robots.